Okay, so we resume from where we left off last time, and now what I was saying was that we need to prove this theorem, and well, we are talking about. So we were talking about the minimal polynomial, and now diagonalizability, and we will prove this theorem relating the two. So before we prove this theorem, which is that a matrix or a transformation is diagonalizable, obviously a square matrix. So I think when we say this V to V is about, this simply means second. Okay. Simply means that V is finite dimensional over F. And T obviously is linear. So T is diagonalizable. So okay, again, you assume that the characteristic polynomial splits as a product of linear factors in F, meaning that it is degree n, let's say, and there are n roots in the field. Okay, then the matrix is diagonalizable, or the transformation is diagonalizable with respect to any ordered well, sorry, with respect to some basis, or any basis. That means there is a basis of eigenvectors for the vector space if and only if the minimal polynomial has no repeated roots. Yes, the minimal polynomial can indeed have multiple different roots, but the roots cannot repeat. Okay, great. So now the proof uses this thing. So let us first, the idea is to first prove this lemma. And the lemma is sort of very strange. It's sort of, how did you come up with this lemma? I don't know myself. I took this proof from, I think probably Hoffman and Kunz's book. I forget. Anyway, the lemma says the same thing. Again, suppose V is a finite dimensional F vector space. T is any linear map. And suppose there are lambda 1 to lambda k such that this happens. Okay. Oh, sorry. Suppose these are pairwise distinct scalars, and there are linear maps EI, E1 into EK, from V to V, such that first of all, if you add up the maps directly, you get the identity matrix or the identity transformation. If you add up the linear combination of the maps EI, you get T, and the EIs kill each other. So EI, if you apply EI and then EJ to any vector, or EJ and then EI, then you get 0. So these EIs are actually what you call projection operators. So so like EI square, we will prove, is equal to EI. So they are the projection of the operator onto some lambda I eigenspace. We will get there. Assuming these three things hold, then P is diagonalizable, and lambda 1 to lambda k are indeed all of the eigenvalues. Okay, so that is what we are going to prove. So let's start with the proof of the lemma. I don't think I have any other comments here. Yeah. So we start, as I said, with some observations. I mean, rather, I told you one of the observations. Okay. So proof of the lemma. Okay. So let's call it maybe ABC or what. Apparently, I'm calling it ABC. Okay. The first observation is that EI equals EI square. Okay, and so you guys can, if you want, you can pause the video and try to figure out how these things prove that EI equals EI square. Well, so okay, so yeah, okay, so now if you haven't paused it, then for those of you who just want to enjoy the show, this is EI times identity. Right? But what is identity? Identity by the axiom 2, assumption 2 is summation EI EJ. And now we know that for every j other than I, EI times EJ is 0, the 0 transformation. Therefore, the only one that remains is EI times EI, which is exactly EI squared. Okay. I can use a different catchphrase as well. Instead of saying, for those of you who just want to enjoy the show, I will use a different catchphrase. Now, the next one is, what is T times EI? So I'm just talking about composing linear transformations. EI square is the composite of EI and EI as linear transformations from V to V to V. And the same way now, T times EI. Well, what is T? T is summation lambda I EI. Let's call this, again, I'll use J instead of I. Lambda J. And again, everything is linear, so lambda J times EJ compose EI. Right? But now again, EJ and EI compose to give you 0 whenever I and J are distinct. So what you just get is EJ we get ei times lambda I, and the rest is 0. So this is equal to lambda I ei squared, but ei squared is precisely ei. So here I'm using a as well as 1, 2, and 3. So maybe I should say here some observations using 1, 2, and 3. So that's what we're really proving. Okay, great. So now, okay, so the other thing I could have said here is probably super easy. They're getting inconvenience. Here's another super easy thing. Yeah, so okay, let's look at TEI applied to any V. So because of this thing, so for all V, for V in V, if I look at T composed with EI applied to V, then this is lambda I EI applied to V. But what is this? This is actually, yeah, this is precisely this. This is literally P of EI of V. That's exactly what composite means, right? It's the definition of composite. So this means that EI of V for any vector V is a lambda I eigenvector. Right? So this implies that the image of EI is V lambda I, the lambda I eigenspace. Okay, so these are just some basic observations, and we will need these observations. Oh, and not only that, oops, I should have said something else here, obviously. I think I need to say that. God, where is my pens? I should have said that the EIs are non-zero linear transformations. I mean, I can also write down, like, I can write down a bunch of zeros. T equals these EIs plus lambda k plus 1 times 0 plus lambda k plus 2 times 0. And that is pretty useless. So let us just make sure that EI non-zero. Yes, EIs are non-zero. I should mention that here in my notes, and non-zero linear maps. Okay, great. So now because I know that EI is non-zero, if a map is non-zero, if a matrix is non-zero, for example, its column space is non-zero. Right? It has rank at least 1. So that means that the image is non-zero. And this is why I want EI to be non-zero, so that the image is non-zero. Okay, so there are at least, so what we do know is that these guys are indeed, so there is at least one lambda I eigenvector. So all of these lambda i's are indeed eigenvalues. We have to prove that they are all the eigenvalues, but certainly now we know that they are eigenvalues. So maybe I should mention that. Okay, so now let me start proving it. So I will leave the theorem, I won't erase it, but I'm going to erase this part. So you should write it down if you want. So now because of this so now D, we now claim, maybe this is not an observation anymore, so I can stop saying D. But the claim is now that the lambda 1, lambda k are all the eigenvalues. So let us first prove that last statement. Okay, so they are all of the eigenvalues of T. Why is that true? So first the proof, the first statement is they are indeed eigenvalues because of C. By C, all lambda I are eigenvalues. Okay. Now suppose there is some other lambda. Suppose there is some other lambda. Okay. Now say lambda is not equal to lambda 1, lambda 2, lambda k, and TV is lambda v. Okay, there is some v. What do you have to show? If so either lambda is an eigenvalue, which we want to show is not the case, or v must be 0. So we want to show that v is actually 0, assuming all these three things and all the three ABC. Where is the okay? I will leave this intact, so I will erase this. Maybe I'll keep this on the side just to remind us. So T equals summation. Where should I keep this? 1 was P equals summation lambda I EI. I goes from 1 to k. 2 was the identity equals summation ei. I goes from 1 to k, and 3 is ei ej equals 0 for all I not equals j. Okay, so these are the three things we will use, plus those three facts, and we want to prove that T is diagonalizable, and these are all the eigenvalues. Okay, great. So now let's do this. Suppose this is true, right? So now let's see. So now we write down the definition of T, which is here. So PV equals lambda. So let's leave this intact. So it implies summation lambda I ei v equals, on the other side it's lambda v, which is lambda times identity times v. So I get lambda summation ei v. Ei of v. Okay, but also what do we know? We know that ei of these are all eigenvectors, right? So therefore we get, let me first of all subtract. So I get lambda I minus lambda ei of v equals 0. But now I can even take the lambda scalar inside here, and I can see that, well, the image of this thing is in lambda I. So all of this guy is in v lambda I, because these are eigenvectors. And we have proved before that if you have distinct eigenvalues, lambda 1 to lambda k are distinct, and then those eigenvectors are linearly independent. Which means, how can a sum of these guys be 0, or that sum of the eigenspaces is direct? So how can the sum of these vectors be 0? Every single vector must be 0. For all I by class. And now because these scalars, so remember that lambda is not equal to those, so we can of course cancel out the non-zero scalar. So we get ei of v is 0 for all v. And now I want to prove that v itself is 0, right? Any guesses how? For all I. And you want to prove v is 0. Well, again, this is again super easy, barely an inconvenience. This is all you do is you use this one. Add them up. You get that v is the summation of ei of v applied to v itself, because this is the identity map. But that is the same as saying summation ei of v, which is 0, which is summation of 0, which is 0. Okay, great. So that's at least one part of it. Proof that the eigenvalues, there are no others. Now we need to show that actually T is diagonalizable. So we need to show there is a basis for eigenvectors. Okay, fine. So now let's see. So now, well, and now the answer is clear, right? If these are all the eigenvalues, I'm going to say that those are indeed all of the eigenspace, and the direct sum is the eigen, is the full space. So what we need to say is, right? Because once the direct sum of these guys is the full space, that means when each of these summands, each of these images has a basis of eigenvectors with eigenvalue lambda I. So the full space has the union of those bases as the basis of eigenvectors and eigenvectors for T, and therefore T is diagonalizable. That is the way the proof is going to go. So let us write this down. Okay, so what is the rest of it? So we claim that. So now I will write down the last part. So now to conclude the proof, so we next claim that that V is equal to, as I said, the direct sum of the images, image of EI, and then you're done, because then each of those guys has a basis of eigenvectors. Therefore, V has the union of those as the basis of eigenvectors. This implies, actually, maybe I should probably have done this slightly differently, so give me a second. I'll write down one line before that. Technically, you should write it after that, but it's better probably to do before. So take an order, so take a basis. Let's see. Should I call it Ni or Mi? I think last time we called it Mi, right? The dimension of the basis. Let me just call it Mi. M. I think that's good enough. Mi is doing in. Okay. So let Mi. So define Mi to be the dimension of the image of Ei. Remember that the image of Ei is contained inside lambda eigenspace. Sorry, I don't know if I said equal to lambda eigenspace, but then I'm sorry. This should be contained in the image. Oh, I said V lambda equals lambda eigenspace, and this is contained, right? So yeah. So the image of Ei is contained in the lambda eigenspace, and suppose that has dimension Mi. Once it has dimension Mi, and I'll write down the basis. Bi equals, let's say, B. How did I? You know this? I think the I was a superscript. Yeah. B, I above and J below. So that first of all, 1 less than I less than K, and then 1 less than J less than Mi. And this be a basis. Image of Ei. Okay, suppose this is true for all I. Now we claim, so after this sentence, I go back to the thing. We claim that V is the direct sum Suppose I can prove this. Suppose I can prove that V is the direct sum of these images of the EI operators. Then what am I going to say? Well, we know what the basis of a direct. So the whole point of the direct sum is that it's a coproduct. And the nice thing about the coproduct was that the basis of the coproduct of vector spaces is, well, one of the bases is the coproduct of the bases of the original ones in the category of sets, which just all that fancy language says is take the disjoint union of these guys for distinct lambda i's, that gives you a basis of this, of the direct sum. This would imply, this implies, or this would imply that the disjoint, so this is the disjoint union or coproduct, I goes from 1 to k, vi. Now each of these guys, I don't know, here maybe I should say this. Remember that each of these guys is an eigenvector for t with eigenvalue lambda I, because this is the basis of image of Ei. And image of Ei is contained in the lambda eigenspace. Therefore, the union of these guys is a basis of V, because that's the property of coproducts. So remember coproducts, I guess. We proved this in class. Let's put it in quotes. And not only is it a basis of V, this basis is actually consisting of eigenvectors. For T. Therefore, T is diagonalizable. So the only thing we need to prove now is this. Once you prove it, then the theorem follows. So why is this true? And this also is some jugglery of I deleted A, B, and C already. Maybe I should have written them beside C, D, and E. Okay, anyway, fine. So the other way to say it, is to actually just directly prove that this is the basis of V. If you prove this is the basis of V, then obviously V is a direct sum of these things. Okay. So let's say, so we'll in fact prove. So in fact, we'll prove the stronger thing. Or this is equivalent. This is equivalent to saying And so apparently that's what I'm proving here. Yeah, fine, let's prove this. And of course, it's eigenvalues. So why is this true? So first of all, this spans V. So claim. So okay. So two parts, right? So proof. So spanning set and linearly independent. So why does the union of these guys span V? Well, because all you do is the following. You write down. So V, take any V, let V be in V. Now you use property 2. V is equal to identity times V. Let me not write identity times V, that's just obvious. Summation EI of V. So summation EI of V, whole thing applied to V, but I will again skip one more step and say summation EI of V. And now EI of V is an element in the image of EI. Therefore, it is a linear combination of these guys. Okay, so this guy is in the span of VI. Therefore, the summation of these guys is being a linear combination is also in the span of the union of the guys. So V is in the span of the union of the guys. That's the proof of the spanning set. That's just easy. Okay, super easy. Okay, now the linear independence is slightly less of a very inconvenience. So, but it's still not hard. So I'll still keep these just in case we need them. But you see, so I've stopped referring to, I should really be saying, that this is by property 2, this 2. But at some point, you sort of stop referring to these obvious things. Okay, linear independence. So why is this set linearly independent? Well, so first of all, so again, let's write it. Now this is a notation heavy proof. Cij, Bij. Okay, fine. So suppose a linear combination of these guys running over all the i's is zero. So say Cij, Bij, and I'll just say I comma j. But that means that the outer summation is I goes from 1 to k. The inner summation is j goes from 1 to mi. This description equals 0. If you want, I can really say that. I'll say it once. Maybe we have not seen this in a long time. So I goes from 1 to k, j goes from 1 to n, I. Okay, so these are scalars and these are, of course, vectors. Okay, and this is the 0 vector in the vector space V as usual. Okay, fine. So suppose this is 0. Now, first of all, I can apply, let's see, what do I apply? Basically, I have to apply some clever choices of these operators, right? To prove that, what do I have to prove? I have to prove every single Cij is 0. So basically, it's enough to prove that this is 0 for every I. Because once I do that, these guys are basis elements of the EI, so they are in particular linearly independent. Once you fix an I, so as long as I can prove this, then this is a linear combination of independent vectors. So it is 0 for every I, this combination. Therefore, each scalar is 0 for every I. So that's the strategy. Now, how do you produce such a combination? I guess what you have to do, yeah, exactly. So basically, let's call this entire thing as something like Vi, which belongs to V lambda I. And the lambda is a distinct scale. So we have, let this denote by. So we have summation I goes from 1 to k, Vi equals 0. Okay, I think we already saw this, right? These are different lambda, these are different eigenspaces. And therefore, you can multiply the product T minus lambda j for overall the j's. Yeah. So by class, each Vi is 0. So j goes from 1 to mi. And these are all eigenvectors for a fixed linear transformation T. So we have seen this result from class that Bij equals 0 for all I. But now these guys are a basis of capital BI. So linearly independent themselves. So that's what gives us. Okay, so that's the end of that. Okay, so that's what this is. That's the proof of the lemma. That this is the basis. The moment it's a basis, of course, then V is indeed the direct sum of the spans of each individual parts of the basis, and therefore, well, each of those is indeed. But well, anyway, it's a basis of V. It's an eigenbasis of V, and therefore T is diagonalizable. That's all we wanted to prove. Maybe I should also write this down here. None of this is needed. Equals VI, V lambda I. So all VI equals 0. Okay, none of these two are needed. Okay, fine. So now let's prove the theorem. So the theorem says that T is diagonalizable if and only if the minimal polynomial has no repeated roots. So first of all, so one of those parts is easier, one of those parts uses that lemma. So let me first, since we just proved this lemma, let's first prove the part that uses that lemma. Okay? That's a slightly longer proof. And then the part that's easy is like, well, fine, maybe since we've all forgotten the lemma by now, I may as well do the easier part first. So the easier part is the forward implication. Okay, so proof of theorem. Let's see. Maybe I'll use some worse pens for now. So first of all, let's prove this. Suppose T is diagonalizable, right? So it has a basis of eigenvectors, and then okay. So actually, I sent an email to you guys recently, right, about something about diagonalizable. So that's the same thing. Let's say there is an ordered basis, D of V, such that what happens? Such that the matrix of T with respect to B, comma B, I'll say it here. This is just a diagonal matrix. And now I think we did this in class. I forgot. Which examples did we do in class? But maybe we didn't. Diagonalizable. What is this? Minimal polynomial. Here. No, we didn't do this example. We did the example where all the lambdas are distinct, but we didn't do the actual example where we did that. Okay, fine. So, okay, now the point is these lambdas are arbitrary scalars, but they need not be distinct. Some of them can repeat. So this is something we did not do. We should have done this. Anyway, fine. We are well ahead of time. So now, okay. Okay. Okay, sorry. So now, okay, consider, okay, let P of X equals product, let's say X minus lambda, where lambda runs over the distinct scalars among lambda. Runs over the distinct scalars among the lambdas. So which means you take each scalar lambda I exactly once, you don't repeat it. Among. So let P of X is equal to X minus lambda product, where lambda runs over the distinct scalars among the lambda. It is clear that P of this matrix is 0. right? Because every time you take a x minus lambda, wherever the lambda occurs, those guys will become 0. The rest of them will not become 0. That's fine. But now, if you multiply over all these such factors, then for every single lambda I is equal to one such lambda. So it will give you. So you'll get for every such factor, you get a diagonal matrix with some zeros. And for every position, there is exactly one factor where you get that as a 0, but that becomes 0. So when you multiply them out, a product of diagonal matrices is always just entry by entry multiplication. So and one of those entries is always 0, therefore it's 0. So I'll leave it to you to understand why this is true, but P of T is 0. So technically P of this matrix is 0, but then that's the same as that. So yeah. Right? So yeah. So yeah, so maybe I should say it correctly. So P, if you look at the P of T, BB, this I didn't actually prove in class, but you should think about why this is true. It is the same as the matrix of a polynomial of T. As long as you keep the bases the same, this is the same thing as saying take the polynomial of this matrix. And well, that polynomial of that is 0. That is what I just told you. Therefore, P is 0. And now the moment any linear transformation with respect to any basis is 0, this means P of T is 0. So you don't need to write it in terms of basis. But now it is not 0 n cross n, it is a 0 linear transformation. Okay, but now what does that mean? Okay, what does this mean? It means that P here is a polynomial which is killing T. So the minimal polynomial of T divides this one. Okay, sorry, and before that, P of T is 0 and P has distinct roots. P has no repeated roots. Okay, so here's a polynomial that kills T and has no repeated roots. Because it kills T, the minimal polynomial divides this polynomial, it divides this. And if this has no repeated roots, then any factor of it also cannot have repeated roots. And so we are done. So this implies P min of T, P min of X, P min comma T of X divides P of X, and hence also cannot have repeated roots. Hence also has no hence also has no repeated roots. So that's how you prove that if you have a diagonalizable map, then its minimal polynomial cannot have repeated roots because it divides a polynomial which kills the map and which has no repeated roots. You can do much better, of course. You can say that not only does P min divide this one, P min equals this one. So that's actually the way to prove it is how I proved it in class for distinct eigenvalues. Suppose you take some specific subset, proper subset of these distinct eigenvalues, and look at that polynomial, well, that polynomial will not kill T. You have to check that. And I think I checked that in class for all the distinct guys. So, but then you can complete that proof and show this in general. Even if these eigenvalues are not all distinct, nevertheless, when you run over the distinct eigenvalues exactly once, that is indeed the minimal polynomial, not just a multiple of them, but it is indeed the minimal polynomial. Okay, so anyway, that is the proof of one half of the picture. Now let's do the other half, and now I can erase my theorem. So now we are assuming that T is a transformation, all the eigenvalues exist, right? So all the eigenvalues exist in the field, and then this minimal polynomial has no repeated roots. Then you have to check this. And the reason why now, okay, this is good that I kept these, because we are going to use the lemma to go the other way. To use the lemma, you have to verify that the hypotheses of the lemma are verified. So it is good to keep the hypothesis of the lemma down on the board, and I won't erase that, but I will erase it. So we will now verify that we will define some E1, E2, Ek, and lambda 1, lambda 2, lambda k. Those lambda is are just the product of the eigenvalues which are given by this assumption. From those lambda is, we will define some E1, E2, Eks, I have not told you what those are yet. And then we will verify that these three things hold. Because they hold, T is diagonalizable. That's what the lemma said. The moment you can verify these three conditions for some definition of EIs, satisfying these conditions, then the lemma says that the T is diagonalizable. That is the other half of the proof. Let us work that out. Okay, so now I will use some other black pens. Now I have to go back. Yeah. Yeah. Okay, so fine. So now suppose we say that so okay, there's two subtleties to the proof. Let me see. Do I want to do k equals 1 case first? So going the other way. Say p min of t or p min comma t of x has no repeated roots. Sorry. Has simple roots. So it's no repeated roots is also called simple roots. Non-repeated roots, lambda 1, lambda 2, lambda k in the field F. There are two cases, okay? The first case is when k is 1. You have to do this separately. You will see why. Okay, but the first case is when k is 1. So, and the next case is when k is bigger than 1. Suppose k is 1. Then what does that mean? What is the minimal polynomial? If k equal to 1 and there are no repeated roots. It is x minus lambda 1. That's it. Nothing else. But what this polynomial kills t. How can it kill t? It means t minus lambda 1 identity equals 0. Now this is readable. Maybe I'll erase it on the next slide. How can it be that t minus what that just means t is lambda 1? And if it is a multiple of the identity, then any basis is an eigenbasis with eigenvalue lambda 1. So of course it's diagonalizable. Hence any basis of V is an eigenbasis, meaning a basis of eigenvectors, and therefore T is obviously diagonalizable. Okay, so this is the k equals 1 case. Now k is bigger equals 2. That is of course the more tricky case. That's the case we need to solve. Okay, so now let's see. So before we go to the proof of that, we are going to use homework. Apparently, it's homework 7 question 5 this time, which is in your exercises. We are going to use the interpolation polynomials. Okay, so maybe I'll just say recall or digression or something. Homework 7 question 5, interpolation polynomials. Also, we will use the fact that the Vandermonde matrix is non-singular. Okay, but so let's see. That was, I forget what homework. Anyway, we will use the fact that the Vandermonde matrix is non-singular. Okay, so what I'm going to do now is I'm going to define. So remember, I want to define these EIs, right? So what is the strategy for the proof? The strategy is this is what I know. We've done before. This is before I took k equals 1 or k bigger than 1. So I know that I have a linear transformation from a finite dimensional vector space V to itself and I know that this is simple root, this minimal polynomial has simple roots. And these may occur multiple times in the characteristic polynomial. But the minimal polynomial has simple roots. I want to show that there exist linear transformations E1, E2, Ek. Sorry, so yeah, these are the simple roots. Corresponding to these, I want to show that there exist linear transformations from V to V, E1, E2, Ek, such that these three conditions hold. The moment these three conditions hold, I know that T is diagonalizable and my proof is complete. Okay, so this will not apply to the k equals 1, which was directly trivial, but now this is what I want to use. So the point is, you need these three conditions to hold. Well, this thing requires k bigger than 1, right? Because ei times ej is 0. Okay, so let's now define the interpolation polynomials. So define pi of x equals product j not equals I, x minus lambda I over lambda j minus lambda I. I think these are the interpolation polynomials. Something is very wrong here. No, this should be x minus lambda j over lambda I minus lambda j. So then what happens at lambda, when x equals lambda I, then this is lambda I minus lambda j over lambda I minus lambda j. It's a product of ones. So this is equal to 1 at lambda I, and at any other lambda j, well, or the lambda I prime, the lambda I prime equals lambda j for some j not equals I, right? So that means that particular factor will have 0 in the numerator. So the whole product is 0. So this is equal to 1 at x equals lambda I, 0 at x equals lambda j, j not equals I. So at every other lambda j, it is 0, at lambda I, it is 1. These are the interpolation polynomials. So let me now do some. So before we actually prove this if and only part, I want to take a digression into these interpolation polynomials. Okay, so I want to first claim that if you add these up, let me just take P1 plus P2 plus Pk, I get 1. Why? So this is a very clever bit of mathematics in some sense. Here are a bunch of polynomials. I know what they exactly equal at all the lambdas, at the k values lambda. Also, do you see the degree of this polynomial? The degree of this polynomial is k minus 1. It is not k. Because we are multiplying k minus 1 factors here. So I have a bunch of polynomials of degree k minus 1. Let me write them down. So degree pi equals k minus 1 for all I. Okay, now that is really the key. So now what I'm going to say is the following. If I add up all of these guys, just take P1 of x plus P2 of x plus P3 of x plus Pk of x. What does that equal at each lambda I? Well, at each lambda I, one of the Pi of x equals 1 and everything else equals 0. So the whole summation equals 1 plus 0 plus 0 plus 0 equals 1. So the summation of these guys is a polynomial of degree at most k minus 1. Maybe some higher order terms cancel, but certainly nothing higher can get created. They can only get annihilated. Right? So some higher order terms may cancel anyway. So as a result, you have this polynomial, this is the summation of these guys, of degree strictly less than k, at most k minus 1, which equals 1 at k distinct points. Right? So if I, for example, look at the polynomial P1 of x plus P2 of x plus Pk of x minus 1, that is also a polynomial. And that polynomial equals 0 at k distinct points. So it has k distinct roots. And the claim is therefore it is identically 0. Because the polynomial has degree at most k minus 1, how can a polynomial of degree 3 have 4 roots? Which polynomial of degree less equals 3 has 4 roots? Or, for example, which linear polynomial has 2 roots? Well, which line has 2 roots? Which line passes through 2 points on the x-axis, there's a unique line which passes through them, and that line is called the x-axis. Right? That means it's the identical. So that what is the x-axis? It is the graph of the function y equals 0. So at every point y equals 0. Similarly, which quadratic polynomial, which quadratic polynomial, which means which parabola passes through 3 points on the x-axis. You can pass through 2 different points on the x-axis. How do you pass through 3 different points on the x-axis? So the only line passing through 2 points on the x-axis is the x-axis. The only parabola. So there are multiple parabolas that can pass like this or like this or like this. But I want a parabola to pass through 3 points. How can that happen? The only way it can happen is if the coefficient of the x square was 0, then the function is 0 and that indeed passes through the x-axis. And that's the point. So you can prove that rigorously for any polynomial of degree at most k minus 1. If it is 0 at more than that many points, polynomial of degree 2 is 0 at 3 points. Polynomial of degree 1, a line, is 0 at 2 points. A polynomial of degree k minus 1 or less is 0 at k points. Then that polynomial must be the 0 polynomial. How do you prove that? That's what we will do after I drink some water. So claim, let me make 2 claims. I want to make 2 claims because I will use both of them. Let's say A, P1 of x plus P2 of x plus so on. Actually, I should make the claims in the reverse order. So this is my claim B. Is identically equal to. When I say identically equal to 1, it means equal to 1 as polynomials. The linear terms cancel, the quadratic terms cancel, the cubic terms cancel, only the constant terms remain, and the constant terms are equal to 1. And A, lambda 1 P1 of x plus lambda 2 P2 of x plus lambda k Pk of x is identically equal, again as polynomials, to T. T is x. Those are my 2 claims. I'm going to prove them first, and then that's the point. Once I prove them, I will almost straightforward get 1 and 2. Okay, so let's see that. Okay, so let's prove. So prove. So I'm saying that this is a digression into interpolation polynomials, but of course it is extremely relevant for this. So this is not some random thing I'm doing. I'm doing it in order to use it to prove those things. Yeah, so prove. So let's prove B first. So, yeah. So let me define a new polynomial. Define g of x to be, so g of x which is a polynomial via via the following definition. G of x is equal to the left hand side minus the right hand side. Definition summation pi of x minus 1. As I said, because of this polynomial here, we know therefore that okay, and we know so degree of g. Okay, so degree of g is less equals k minus 1, right? Let us write this down. Let us write this polynomial down. Right? G of x equals, let's say, c naught plus c1 x plus c k minus 1 x to the k minus 1. And some of the ci's can be 0. I'm not saying that the degree is exactly k minus 1. This can be 0, this can be 0. I'm in fact going to claim that all of them are 0. Right? Okay. What do we know? We know from above, from this thing. Maybe I should say star here. By star, we know that g of lambda 1 is 0 because p1 of lambda 1 is 1. Everything else is 0. P2 of lambda 1, P3 of lambda 1, everything else is 0. So 1 plus 0 plus 0 minus 1. That is 0. And the same way g of lambda 2 is 0, g of lambda 3 is 0. Now, by star, g of lambda 1 equals g of lambda k equals 0. Write this down. I.e. Okay, now here we go. So How do I want to write this down? Yeah. So 1 times C0 plus lambda 1 times C1 plus lambda 1 square times C2 plus lambda 1 to the k minus 1 times ck minus 1 equals 0. 1 times C0 plus lambda 2 times C1. This is the g of lambda 2 equals 0. Plus lambda 2 square lambda 2 to the k minus 1 ck minus 1 equals 0. And you keep going, you write all of them. 1 times C0 plus lambda, now this is lambda k times C1 plus lambda k square times C2 plus lambda k to the k minus 1 ck minus 1 equals 0. This is a system of linear equations. And so we come back, since this is linear algebra class, we go back all the way to lecture 1 and learn to write this down as a system Ax equals the 0 vector. Rewrite this as what? What is the matrix? So my unknowns here are C0, C1, C2. My knowns here are the one through lambda, the lambda 1 to lambda k. So it is 1, lambda 1 square, lambda 1 to the k minus 1, 1, lambda 2 square, lambda 2 to the k minus 1, 1, lambda k square, lambda k to the k minus 1. This is a square matrix, also called the Vandermonde matrix or maybe X transpose, times the vector C0, C1, C2 even if you want, ck minus 1 equals the 0 vector. What does that give you? But now we know that this matrix is non-singular. Why do we know that? Because we had a homework problem that calculated the determinant of this matrix, and the determinant was the product of lambda I minus lambda j. So because these lambda i's are distinct, lambda I minus lambda j is non-zero, the product is non-zero in any field. Product of non-zero scalars is non-zero. It has a reciprocal. And therefore this matrix is non-singular. So by homework, this is non-singular because the det is non-zero. Well, that is it. This det of this equals non-zero. But that means if you have Ax equals 0, and by invertibility, the only solution is x equals 0. So all Ci's are 0. So all Ci's. And that is exactly the same as saying Gx is identically 0. And this is G is identical. And that's what we wanted to prove. That if Gx, this minus 1 is identically 0 as a polynomial, then this is identically 1 as a polynomial. Right? So the trick is to use this generalized, the trick is to use this Vandermonde matrix. And that is, so that's why I asked you guys to, I asked you guys at homework a few weeks ago, because we will use it here, to prove that this matrix is invertible because its determinant is non-zero. So yeah, so this is also this is the standard reason why in any field, if you have a quadratic polynomial with 3 roots, that polynomial is 0. Or in more generally, any polynomial is uniquely determined by its values at k points. So even if I knew the value of this lambda 1 equals alpha 1, and the value at lambda 2 equals alpha 2 and alpha k, then I would get this times this equals alpha 1, alpha 2, alpha k. It's a known vector, therefore I can take A inverse and I uniquely get the coefficients of the polynomial. So every polynomial of degree at most k minus 1 is uniquely determined by its values at k distinct points. If the values are 0, then the polynomial is 0. If the values are anything else, the polynomial is uniquely determined. I don't know what it is. In this case, of course, we wanted the polynomial and it's identically 0. this minus 1 is identical to 0. Okay, great. The same basic proof goes true for A, so why don't I tell you that proof? We have half an hour, so. How much more after this? Well, we'll see how far we go. I basically gave you a 1 hour lecture last time, so I'll probably catch up this time. Okay. Okay, so this was part B, part A. Part A is roughly the same thing. Let's define h of x to be that minus that. Define h of x to be that. H equals on that left hand side minus right hand side. And this is where I crucially need. So what do I know here? I know that the degree, I want to again say the same thing, that h of x is going to be something at k distinct points, and its degree is strictly less than k. Its degree should be less equals k minus 1. But you see, I don't know if this is all a linear, so what if k equal to 1? Then these p of i's would have degree 0. This would have degree, the whole thing would have degree 0. And this would have degree 1. And 1 is not less equals k minus 1 if k equal to 1. So when k equal to 1, this degree is not less equals k minus 1, it is equal to k. And that is why I need k bigger equals 2. So in this proof, you remember, I started the proof of the theorem by first disposing of one implication, the forward implication. In the backward implication proof, I first disposed of the case when k equal to 1. And this is why. Now I use the fact that k bigger equals 2, therefore this degree is less equals k minus 1. Since k bigger equals 2, the degree, each of these guys has degree at most k minus 1. This has degree 1, which is still at most k minus 1 because k is at least 2. And therefore the degree of h is less equals k minus 1. And now I can play the same game as above. Okay. Now check. Moreover, h of lambda I. Let's take the sum from j equals 1 to k, not I, because I'm doing h of lambda I. So I get lambda j pj of lambda I minus lambda I. But now again, I know that this is equal to what one calls the Kronecker delta, right? Delta ij. I think I told you last time. Delta ij just means it's 1 when I equal to j and 0 elsewhere. So all the j not equal to I terms go away. And this is just lambda I times 1 minus lambda I, which is 0 for all I. So here is a polynomial of degree at most k minus 1, which is 0 at k different points. And therefore, by the same trick as above, the polynomial is identically 0, and therefore we are done. So by the same argument as for B, repeating the argument for B. So this proves the claim. Okay, that the P1, so if you take the interpolation polynomials for lambda 1, lambda 2, lambda k, and define, and then the summation of those polynomials is identically 1, and the summation of lambda pi of x is identically x. So this proves the claim. The claim is proved. The claim follows. Because now we return to the proof. We define the operators E1, E2, Ek in the obvious way, and then we just prove this. So if I want to take x equals summation lambda I, you know what I have to substitute for x, and that's exactly what we do. Okay, so now continue back to the proof. So back to the proof of the theorem. And in fact, the proof going the other way as far as I remember. Let me check, but I think that was the correct thing. Yeah. Okay, yeah, so these are defined. Now let us finally define the EI. So, and the EIs are precisely PI, the interpolation polynomial, evaluated at the T. the original linear transformation. Remember, what are we trying to do here? We are given a linear transformation, all of whose roots lie in the ground field, and whose minimal polynomial over that field has simple roots, has no repeated roots. So those simple roots are lambda 1, lambda 2, lambda k, pairwise distinct, with k at least bigger or equals 2, k at least 2. So far, what have we done? So far, we did not touch that transformation. We did not do any of this. We just looked at some interpolation polynomials and proved some nice properties of those using the invertibility of the usual Vandermonde matrix. Now I will use those interpolation polynomials, apply them to T, and get my maps EI. Okay, so define. So let's say given T as above. As in the theorem, as in the statement, with P min T of X having simple roots, lambda 1 to lambda k. First of all, I have those interpolation polynomials for these lambda i's, and now I define my EI's. So define EI to be EI, which is again, of course, a linear map from V to V. EI is Pi of T. That is my definition. The claim is that 1, 2, and 3 now hold for these EI's, and therefore I'm done. Therefore, T is diagonalizable by the lemma. The lemma said that if 1, 2, and 3 hold for linear maps EI, then the transformation T is diagonalizable. And that's what we want to prove in the theorem in this other implication. Okay, so let's do this. 1 and 2 are already done. The nice thing is this interpolation business already finished 1 and 2. So proof of a claim. These EI's, the EI, and the lambda I, and the T, of course, all of these satisfy 1, 2, and 3. By 1, 2, and 3, of course, I mean these 1, 2, and 3. And therefore, by the lemma, T will be diagonalizable. So it suffices to prove the claim. Once I prove the claim, the lemma takes over and T is diagonalizable. So why do we satisfy 1, 2, and 3? As I said, 1 and 2 are trivial. So it's enough to prove the claim. So proof of claim, which is the end of the proof. That's why you see I stopped last time with stating the lemma and the theorem. I could have gone on for half an hour more and tried some of this, but I'm already 1 hour past. So it's much better that I stop there and do it here. Because even the ingredients of the lemma were sort of, those EIs, I would have to remind you of some linear maps, EI and this and that. Better to just do them together. So, proof of claim. Okay, proof of the claim is the following. So first of all, okay, let's do 1, 2, and 3. So 1. Summation lambda I is calculated. This is summation lambda I pi of t. But by the previous, maybe I should call this claim 2. And I call the previous one claim 1. Okay, let's put a number claim 1. So proof of claim 2. And now, but we know what is lambda I pi of x summation. That is equal to x. Claim 1 and then the part B is the summation lambda I pi of x. Sorry, maybe I should have said that here. Equals summation lambda I pi of x, whole thing evaluated at p. And that by claim 1b is exactly x. evaluated at t, which is just t. Part 2. Again, the exact same thing. Summation ei, summation pi of t. Okay, now I can erase this. Now I can erase this. Because now we've proved it. Okay, and that is equal to summation pi of x, whole thing evaluated at t. And again by claim 1a, something is very wrong. This was claim 1a, wasn't it? This must be claim 1b. I made them parallel, so yeah. This is just 1 evaluated at t, but the 1 evaluated at any linear transformation is precisely identical. Okay, the third one is the key, so that's the only remaining thing, but I'm sure we can finish it in this board and end the theorem. So y is, if I take ei times ej, I'm multiplying this times that. And that's right. So let's say, let me just take e1 times e2, okay? Let me take e1 times ek, just for fun, just to show you how this works. And the actual proof is exactly the same, except that the notation gets trickier. But let me show you how this works. What is ei times ej? E1 times ek. It is p1 of t times pk of t. What is p1 of t? It is product t minus lambda j. J is bigger than 1. So j goes from 2 to k minus 1. Sorry, 2 to k. Oops, I should give it this one better. Let's write that. Whatever, t minus lambda j identity divided by some scalar. I don't care about the scalars. Okay, some scalar. I can say that also. Lambda 1 minus lambda j times the product t minus lambda j identity over lambda k minus lambda j. J now goes from 1 to k minus 1. Okay, so I don't care what else happens, but you see, every factor from 2 to k is mentioned here. Look at this, the numerator factors with t. Every factor from 2 to k is here, every factor from 1 to k minus 1 is here, and k is at least 2. So the k equal to 1 factor, j equal to 1 factor occurs here, every other j factor occurs here. So it is at least one of each kind always already occurs. This is equal to some scalar in the denominator. So scalar times the product j goes from 1 to k, t minus lambda j identity, times product from j goes from 2 to k minus 1. I took the 1 part here, so 1 to k, and then this starts from 2 to k minus 1. T minus lambda j identity. Okay, now I don't even care about the scalar, I don't care about this factor. Just focus on the term in the middle. What does this equal? Take a moment and think about it. What is this? Remember what the minimal polynomial was. Maybe I should write that down somewhere. Here, there was a red pen. Pmin. So in this implication, I know that Pmin of x equals x minus lambda 1 dot x minus lambda k. So Pmin comma t. The minimal polynomial of t was this polynomial. This is exactly this polynomial here. Evaluated at t. What do you get when you evaluate the minimal polynomial of t at t? You get 0. And what do you get when you multiply the 0 linear transformation by anything, and when you compose it with anything else, you still get the 0 linear transformation. Times ek is equal to the zero transformation. I could have taken EI times EJ. All that would be missing is that would change is that in this term there is no I term here, and in this term there is no J term here. So I would still get the full set of factors, and the restricted set of factors where instead of 1 and k being missing, I and j would be missing. But I don't even care about this set of factors. I just care that I have one copy of each factor, so I can get the full minimal polynomial, and that is 0. Therefore, the function is 0. And so EI times EJ is also 0. Summation EI is identity. Summation lambda EI is t. Therefore, the three conditions of the lemma are satisfied, and therefore, by the lemma, t is diagonalizable, which is what we say. That ends the proof. That ends the proof of the claim 2. Therefore, by the lemma, it ends the claim of the theorem. The reverse implication is that if you have such a polynomial with the lambda is distinct, then t must be diagonalizable, and that's by the lemma. Okay, so that was a long proof because it involved a lemma, it involved some excursions into those interpolation polynomials, and using the Vandermonde matrix to cleverly prove that if you have a polynomial of degree 5 that is 0 at 6 points or more points, then that polynomial is 0. And so, yeah, but all of that sort of comes together in this nice symphony of ideas, and we are done. Okay, the next thing I want to prove is something about simultaneous diagonalizability. So suppose we have matrices which are, so suppose I have two matrices which are both diagonalizable. So each of them has a different basis of eigenvectors, but I also know that A times B equals B times A. Then you can actually prove, and we will prove it next time, I guess, that A and B have, you can write down a common eigenbasis with respect to which A is diagonal and B is diagonal with respect to the same eigenbasis. So that's the non-trivial part. I think so. My plan today is to now do some. So before I prove that again, just like the lemma, I required that lemma to prove the theorem, and I required these interpolation polynomials to prove the theorem. This time I won't put them as part of the proof. Let me just first do all the preliminaries right now, and then I will state the theorem about proposition about simultaneous diagonalizability, and then I will end the lecture and we will prove the proposition next time. Okay? But this time the ideas are slightly easier to sort of teach in a different lecture, so I'll do it next time. I'll prove it next time, but the preliminaries are today. So take a moment if you want to take a look. I'm going to erase the entire board, that entire board. This can stay. I will also drink some water. I said towards simultaneous diagonalizability. And I should point out that I said if you have two linear transformations which commute, then they can both be simultaneously diagonalized. It doesn't. The word two is not important. If you have 5 such transformations which pairwise commute, the same thing happens. If you have infinitely many, any set of such transformations which pairwise commute, then they can be diagonalized. So even 2 or finite is not even the key. The commuting is the key. Okay, so we will get there. Fine. For now, let's see. First, what I want to do. So the preliminary results. So definition. So suppose I have a linear transformation of a vector space, not necessarily finite dimensional, and I have a subspace. We say that the subspace is stable under the linear transformation if basically T takes W to W. Yeah? So say W containing V are F vector spaces. And T is a linear map from V to V. We said W is T stable. It's or stable under T. If T of W is contained in W. Okay, so that's we have actually seen something like this earlier, but fine, we are not defining it this way. So let's take an example. Let's say V is just, I'll look at an actual matrix as a transformation. So it acts on set of 3 by 3 vectors. T is the left multiplication by the matrix, let's say 2, 2, that we can call this lambda, 0, 0, 0, 0. Okay, of course, V is this thing, and let's say W is the span of E1 and E2. Let's see what happens. Right? So let's say I take any vector in W, so add by 2, 1, 2, lambda, 0, 0, 0, 0, 0 on the span of E1 and E2. So I take 0. Let's check, that's very bad. Right? So of course, I do row times column, so twice A plus B, twice B, and lambda times 0, 0. So indeed, this is again a vector in the span of E1 and E2, so that's what we're done. So that's what it means to be T stable. You can also check that the span of E3 is T stable. But fine, I'll not do that. Okay, so here's a lemma, and then there is some claim, and I think, yeah, this is good. Where should I put the lemma? I can put it here probably. Why not? Okay, lemma. Suppose I have a. Okay, now suppose this is all true and V is finite dimensional. Say W containing V are finite dimensional over F, and T is in lim VV, and W is T stable. Which means that T takes W to W. Right? So it takes the vector space V to itself, but it also takes W to itself. Then you can talk about the characteristic polynomial of T as a transformation of V and as a transformation of W. You can talk about the minimal polynomial of T as a transformation of V and as a transformation of W. How are these polynomials related? That's the question. And the answer is, we have seen one of them at least. I think the characteristic polynomial we sort of saw earlier, but let's do this formally. The polynomials for W divide the respective polynomials for V. That's the statement. Then A, the characteristic polynomial for W divides the characteristic polynomial for V, and B, the minimal polynomial for W. I don't know what to say. These are the two statements. The characteristic polynomial and the minimal polynomial both for W divide the one for V. Okay. Let's first prove, I guess. So apparently the minimal polynomial is easier to prove. That's clear. So let's look at, let's evaluate the minimal polynomial of V at T, but on W. So evaluate or compute or whatever P min of V applied to T restricted W. Okay? what does it equal? Well, the point is, since P min, I'm sorry, of V kills T on all of V. It kills T on W. It kills T on a bigger vector space. Therefore, this is 0. P min comma V of T W is 0. Therefore, P min V, therefore this guy is a polynomial which when applied to T on W kills it. Whenever a polynomial kills a transformation, it must be divisible by the minimal polynomial of the transformation over that vector space. And therefore we are done. As far as the characteristic polynomial goes, now we do a little more work. It is still almost super easy. By the way, I mean, I should, for those of you who know where super easy paired inconvenience is, I have been seeing those videos for quite a long time. I didn't just see them yesterday and pick up this one. Somehow I never used it before. Yeah. So characteristic polynomial of T on W and T on V. I think here I might need to take the eigenbasis. Yeah. This is the proof that we have seen before in some sense. Let V prime be an ordered basis. Let me use a different pen now. So this one. Let V prime. Do I want to number them as well? No. Equals ordered basis of W, and now we will extend it to an ordered basis of V. Extend using, let's call it, let's say V double prime to an ordered basis of V. First you put B prime, then you put B double prime, and extend the original ordered basis of W to an ordered basis of V by attaching some more other vectors. Okay, now so let's maybe do an example. You saw this example here. Let's do this example. Let's call this as a B prime, and then so for example, B prime equals I'll just say all of these things. So B is F3. If I tell you what is B prime, then you know what is W. It's the span of B prime. E1, E2. So W is therefore the span, and B double prime is E3. And clearly these together make up an ordered basis of V, and this is a basis of W. Wait. And I also know that T is this thing, right? Then with respect to this basis, T is actually upper triangular, but more specifically it is block upper triangular. I mean, so of course this is just a standard basis, and this is exactly the matrix 2, 1, 2, lambda. Yes, and indeed it is. In fact, it is upper triangular as well, but that's sort of a bit misleading. It's block upper triangular. Okay. Now I want to say that the same thing happens in general. This is just an example, which I'm enclosing between some box maybe. But now let's return back to the proof. So let B prime be some order, any ordered basis of W. Extend, and the point is W is T stable. We are given that W is T stable. Extend to a ordered basis of V itself using some other remaining set of vectors. Since V is finite dimensional, everything here is finite. All the sets here are finite. Okay, great. The claim is that then, so the matrix of T with respect to B is block upper is. Let's check why. This is just notational. This is just notation. In fact, so more, I can even be slightly more precise. In fact, if you write down TBB, P, Q, you will get this is 0 and R, where P is of course with respect to B prime and B prime. And P is precisely the matrix where P is exactly the matrix. Look at the P matrix restricted to T transformation restricted to W, because T is W is T stable. So this is indeed a linear map from W to W, and take the coordinate matrix with respect to B prime and B prime. Yeah, and that's what it is. So, I mean, a priori this is a matrix, and each entry of the matrix is the coefficient of some basis when you write T of some other basis vector, right? But the point is, in fact, this whole set of coefficients itself is a matrix of the form T, B prime, where T is restricted to W. So this is the first upper matrix here is indeed the coordinate matrix of a linear transformation on W. That's what we're trying to say. It's not just a set of all coefficients of T acting on something to something. It is the coordinate matrix of this linear transformation acting on W with respect to the ordered basis B prime. Okay, so how do we prove this? I think you have to prove this, and then maybe not. So this is the proof is check yourselves, because I think we are 3 minutes, 1.5 hours. So, but basically we have seen this in class, and therefore, but now let's look at the characteristic polynomial of T. So the characteristic polynomial of T is the same as the characteristic polynomial of this matrix with respect to any ordered basis, in particular this one. So P T V of X is indeed the det of X ID minus P, 0 minus Q, 0 minus 0, and X ID minus R. And we know that this being a block upper triangular matrix, and since determinants exist over any ring kind of thing, a commutative ring, so we look at the ring of polynomials in Fx. The determinant of a block upper triangular matrix or a block triangular matrix is the product of the determinants on the diagonals. This is again from class. Det xid minus p times, I should take a new pen maybe. Now I don't care what this polynomial is. It is something. But what is this polynomial? This is exactly the polynomial, characteristic polynomial of T restricted to W. P T W of X times this thing. And therefore, we started with the polynomial of V, characteristic polynomial of T on V. We find that it is a product of the characteristic polynomial of the same T but on W, because W is T stable, times some other polynomial. Therefore, this thing divides the left hand side. That's what we wanted to do. So the minimum polynomial divides it rather easily. The characteristic polynomial does with slightly less ease, but because there's a check here that I didn't do, but you can do that yourselves. That's fine. And so now finally we come to the statement of the theorem. I will state the theorem and I will stop. So it took exactly, basically 1.5 hours. I thought it would take longer, but not really. That's fine. you replace this as well. Okay, so let's write down the theorem and then we will stop. Next time we will prove the theorem on simultaneous diagonalizability. Apparently I'm calling it now. Okay. Okay, so again, suppose what we crucially need here is that V is finite dimensional. A finite dimensional vector space over a field F. And as I said, I don't need two linear transformations. I don't need finitely many linear transformations. I can take an arbitrary set of linear transformations from V to V, which are pairwise commuting. Okay, so let's say are all diagonalizable. Okay, if the T pair are pairwise commuting as well, if Ti Tj equals Tj Ti, Ti composed with Tj equals Tj composed with Ti for all I naught. So what does composing mean? It means that you're looking at maps again. The composite on both sides are maps, linear maps from V to V. Assuming these two sides give you the same linear map for every I naught equals j, then there exists a common eigenbasis. If this happens, then there exists a basis of V consisting of simultaneous eigenvectors, meaning there are eigenvectors for all of these transformations. Of all Ti. And that is where we will stop. So next time we will start by proving this theorem. Okay, you can take a final look and I will stop the recording.